Good evening, everybody. My name is Steve Baker. Like it says on the slide, I work here at LiquidWeb, and tonight I want to talk a bit about world domination with Perl. What it's really going to be about is how to control the world around you with Perl. Therefore, then you can dominate it. As an example, suppose you have a light. I got one right here, and you want to turn it on. You want to use Perl to do it. How do you do it? Well, if you can control a light, you can control anything. You can do some home automation. You can do some robotics. You can do data gathering. In other words, you can dominate the world. Who laughed? All right, now to do that, we're going to use a Raspberry Pi, which is what we have right here. A better picture of it, though, is up here. Uses an ARM processor, Broadcom 2835 system on a chip, which pretty much the whole thing's on there. There isn't much else. If you look at the board, there isn't much else on there. Runs Linux, and it usually runs Raspbian, which is a version of Debian, and I'm running Occidentalis, which is based on Raspbian. It runs at 700 megahertz. You can overclock it if you really want to. Has 512 megabytes of RAM if you got one recently. Mine only has 256 megabytes. Uses a SD card for storage, no hard drive, although once you boot it off the SD card, you can plug in a hard drive through the USB ports, and it costs 40 bucks. When I made this slide, it cost 35 bucks. But I checked the price today and it was 40. So, I should point out that what I'm going to demonstrate today, I said controlling the world around you. I've got some little circuits that I've plugged in here. There's nothing really complicated here. It's very basic electronics and pretty basic Perl. Now, however, if you have any questions, please do give me, please ask the question right away so I don't say anything weird. Okay, the neat thing about the Raspberry Pi is not that it's a little Linux computer, which is pretty cool by itself, but it's got this connector on it that it brings out the general purpose I/O pins. You got a whole bunch of pins that you can set to high or low, or you can read whether there's a high or low on it from an external source. In addition, you can do a few other things with some of the pins. The yellow ones up there, I can't read the numbers from here, they are a serial port. The blue ones are I2C protocol. The purple one's SPI protocol. Pin 12, which is the one right under the yellow ones, can also be used to do pulse width modulation, which we'll be talking about in a little bit. Occidentalis Linux. This is the version I'm running here. It's based on Raspbian. The difference between it and Raspbian, and the reason that I'm using this particular version, is that it has kernel modules for common electronic devices loaded. I'm not actually using any of those devices in any of my demos tonight, but they're there. It includes the I2C and the SPI and one-wire support. It's got a number of little convenience features like SSHD starting when you boot up, which you have to go configure in Raspbian. It runs Perl. It has Perl 5.14.2 on it, which is a cool thing, except that Perl is not real popular in the Raspberry Pi community. Most of the demos you see, most of the examples you find are in Python or in C, mostly Python. But I didn't want to do any Python tonight because, dang it, it's a Perl users group. And also because, as has been documented elsewhere, Python is dangerous. Yeah. All right. I want to run over a quick little bit about how you set up the system. Like it says, easy, very easy to do. You're basically just downloading the OS image, stick it in the Raspberry Pi, and turn on the power. The only hard part, the only slightly tricky part, is actually getting the OS image onto the SD card, because how you do that depends on whether you're running Windows, Linux, or Mac, or something else. That link there, which I'm sure you've memorized by now, is has got the full instructions for installing the latest version of Occidentalis, unless they've come up with a new version since then. You might laugh about that, but many of the, I just did this a couple weeks ago, and many of the modules that we'll be looking at here have been upgraded since then, it turns out, by several versions. That just gets the Raspberry Pi running. Now, next thing you got to do is upgrade GCC. There's the steps, it's easy. The reason you have to upgrade GCC is because you needed to compile this library. This is a library that is used to communicate with the system on a chip. Simple instructions there, nothing complicated. But then you get to the Perl module that's basically just a wrapper around the BCM 2835 library. This one had a little trick to it right here. I installed it manually rather than using CPAN because I found a bug in that it would install, but it wouldn't pass the test, and it would kind of work if you installed it, but it didn't work for everything. And the reason was that -LRT at the end, it needs the libRT. I let the guy know that maintains the library, and probably this is one of the things that's been upgraded since then, so maybe he's fixed it by now. But this is how I had to install it. Okay, as I said, device BCM 2835. It's a wrapper around the BCM 2835 library. Provides functions to read the GPIO pins. And it's your basic method of communication with the outside world that you want to dominate. As it says, major limitation here, there are no interrupts. If you're going to look at these pins, you have to poll them. So you got a little loop sitting there running, watching for changes. Interrupts would be nice, but they're not there. These are some of the functions that we'll be using in this module. Not much to them. Basically, there's one to set the pin configuration, set it up for input or output. We can set the logic level of a pin. We can check the logic level of a pin. And then there's some SPI operations that I will get to later, SPI being a protocol. Any questions yet? Am I talking too fast? Talking too slow? All right.
Why is there, what is GPI write? How is GPI write different? That's so you can just set a variable which will set high or low?
Sets it high, clear, sets it low, write, you pass a variable that you can set. It's useful in some situations, just a convenience function. We've got some power considerations. First of all, power for the Raspberry Pi itself. It's powered through a USB port. It's actually powered through a USB connector, not through one of its USB ports. But it draws 700 milliamps. And a standard USB port supplies 500 milliamps. You can plug it in on your USB port in your computer. It might work. I plugged it in to mine. It worked until I started typing, and then the keyboard would start acting really strange. I would have it'd start repeating keys, and the problem turned out to be the power. So you need I stuck a 1 amp power supply on mine and run it off of that. Works much better. Also the voltage. The voltage, of course, it's USB voltage coming in, but the pins, the GPIO pins are 3.3 volts. That's what it's supplying, and that's what it expects to see if you're going to apply a high on those pins. Not 5 volts. A lot of the sensors that you might want to use are 5-volt sensors. If you're going to use those kinds of things, you need to do the appropriate level conversion before you tie it to the Raspberry Pi, or you'll blow it up. Back to current. Yeah, you don't want to blow it up. Back to current. The pins can only source about 16 milliamps. That's not a lot. You're not going to dominate much world with 16 milliamps. You're not even going to make your robot arm move very well. And there'll be some ways I'll show you to get around that here in a minute. It is enough to drive some little lights that we can make blink here in a little bit. Connecting an LED. An LED is a little light bulb. Not an incandescent bulb, but an LED. Very straightforward. You just connecting it to a pin, one of the GPIO pins, connect it to ground through a resistor. The resistor is just there to limit the current. Connecting a button, slightly more complicated. You're going to be, you want to supply a low or a high depending on whether the button is pressed. This is going to supply a low normally and a high when the button is pressed. The GPIO pin is tied to ground through that 10K resistor. And the only reason the resistor is there really is so that when you press the button, you don't short your 3.3 volts to ground. But other than that, there's a low on the pin when the button is open and a high on the pin when the button is pressed. Those are the two basic circuits we're going to look at first. And now we can look at some Perl code. Let's see here. Okay, first of all, Perl's pretty simplistic too, just like the electronics. This is an LED class, a little class that I made. What's that?
Blow it up a little bit.
Ooh. I don't know how to blow it up.
Apply more voltage.
No, 3.3 volts only. Not that much to see. It's a pretty simple thing. Yeah, it's not working. If it were a browser, it would work, but it's VI.
Yeah, I think VI actually have to change the font to the menus.
Yeah.
Maybe it does.
So all we're doing here is we're basically creating an object to control the LED. We're passing basically a pin number. We're going to pass big long constants that represent pin numbers, but I think just the numbers actually do work just fine. We've got a few other things we're sticking in there, and they're mainly to make it blink, because we want it to blink. It's cooler when it blinks. Little method here to turn the LED on, another method to turn it off. All we're doing in this case is we're calling that function that we said earlier was setting the state on, setting the state off. We're also updating the time we did that. That's for blinking later. Then we have update blink, which goes through, and because you're going to be cycling through this because you're polling, there's no interrupts. Cycling through and turning the LED on when you want it on, turning it off when you want it off at whatever rate you want it to be. And there's a few little convenience things there for getting the state. You can name your LED after a color, whatever you happen to like. The button class, very similar, only shorter. Basically, we're passing in a pin number, so we tell it what pin the button is on, and then you can find out whether the button is pressed or not, if the get state button. This is our demonstration circuit. That's what you see if you come up and look at the board. That's a little hard to figure out, so there's a little better diagram, although with this low resolution screen it's awfully hard to see even from here, so I'm sure you can't see it that well. But you can see that these are the buttons set up very much like I showed earlier. There's your LEDs set up very much like I showed earlier. This is an A2D converter, which I will get to in a little bit. And way over here is a little servo motor, which we'll also be getting to. This is the pin, this pin with the switch on it that's going to one of the LEDs in the servo motor is the pin that does the pulse width modulation that I was talking about earlier. And because I want to use that pin for both, I just stuck the switch in there to make the demo go nicer, make it easier. So, let's do something. Let's make it do something cool, reasonably cool. First of all, we're creating our objects for our red, yellow, and green LEDs that we have on the board. We're creating objects for our top, middle, and bottom button that we're just going to sit in a loop and make it blink and then watch for the buttons. And the only thing we're watching for the buttons for is to display on the screen whether they're on or off. Nothing real impressive there, but it is cool. Let's run it and see what it does. Okay. Last time we unplugged it, I forgot to set the system back up. This will take a second. Okay, there's one other thing that I failed to mention, and that is that only root can access the GPIO pins. So all of these programs we're going to show you are going to be running as root. Something to keep in mind. Are the lights blinking? The lights are blinking. What's that?
You don't look like you're root.
There's some code in there to make it be root. I tried setting the SUID bit. That doesn't actually work. I don't know why it doesn't work, and it keeps unsetting whenever I check stuff into to Git. So there's just a little chunk of code in there that reruns itself if it's not root as root. So all it's doing there is, let me go back to the code. We set this, the red LED should be blinking and should be, there we go, on for 750 milliseconds, off for 250 milliseconds. And the other, I gave them random amounts to blink. So every time I run it, it'll be different and therefore cool. Wow, that's my Hello World program for Raspberry Pi LEDs. Now,
I know. Seriously.
if I press the buttons, you can't see. It says that the button is on or off. And depending on what button it is. And if I press both the top and the bottom buttons, the program ends. It's cool.
So because you have to pull it, so the button event, you don't get, it's not like mouse button down, mouse button up. What you get is, it's on, and now I notice that's off. And
Right.
it's off, now I notice that's on.
Right.
So when you see the transitions, that's it.
If you are not watching if you put a delay in the loop and you press the button really fast, it'll miss it. Now, there are a set of functions that are part of that module, part of that library actually, that the module is a wrapper around, that improve on that a little bit. They will watch for example, a leading edge or trailing edge transition. There's several ways to set it up. And then you can see whether one has happened since the last time it checked. That didn't actually work in my demo programs. It turns out that there's a problem, I believe, with some type of conflict with Occidentalist distribution. It works apparently under Raspbian, but not Occidentalist. Probably because of those extra kernel modules causing some kind of conflict. Still looking into that. So right now we're stuck with very basic polling. I got another program here. I don't know what it's doing over there. I'll read the code and see. Stop that. Oh, this probably isn't doing anything. As you can see, we're doing just what we were doing before. We're setting up the red, yellow, and green LEDs with the pins they are on. We've got, and they're not as complicated looking this time because we don't care about blinking. Top, middle, and bottom buttons. And all that's going on is if you go over here, you can watch the LEDs. If I press the top button, the red one goes on, middle one yellow, bottom one green. That's all there is to it. Press all three, the program should end. Not all three, but the top and bottom. As you can see, it's not particularly impressive what I'm showing you, but what I am showing you that is kind of cool is that the same basic circuit now works two different ways. The only difference is the program. It's the Perl program that's actually affecting how this works. You can do a whole bunch of things just by changing the program with that very basic circuit. Someone was asking me earlier about setting up an alarm system. Well, the switches are exactly how you would set up an alarm system. It switches on your doors, the windows and such. Just hook them up exactly that way. And then write your program to dominate the world with it. Okay, now the pins are digital. They are not analog. So how do we vary the brightness of the bulb if we want to? Look at the title of the slide, pulse width modulation. Now, you can do pulse width modulation on any of the pins. One of the pins supports it through hardware. And the reason that we're going to use that pin, and if you have that available, you should use it, is because Linux is not a real-time operating system. It'll be hard to get the timing exactly what you're looking for if it's trying to do some type of context switch or garbage collection, or it's doing something strange. So we're going to do the hardware pulse width modulation. Pulse width modulation, what that means is, for those that don't know, is rather than just send it a high, the bulb is on. That's what we were doing before. If you send it a square wave, so it's on part of the time and off part of the time, it'll appear approximately half of the brightness if it responds linearly. If you make the frequency of that fast enough, I got it set for 100 hertz, then you can't see the flicker. If you have it on less, of course, the bulb will be very dim. If you have it on a greater amount, the bulb will get brighter. So we've got some classes for that, of course. Okay, pulse width modulation does a couple of things on the Raspberry Pi. How you do it, how you control it, is you actually write to some files. You write the values you want, or you read the values that you want out of the files. This is the very basic. What we're going to do, this is where the files are, is in that directory there. Should have put this up near the top. Here's some code to read and write those files. And then we have a activate and deactivate, basically to turn pulse width modulation on or off on that pin. And to activate, you basically write a 1 to a file called active. To deactivate it, you write a 0 to it. That's all there is to it. Now, as I said, it does a couple of things with pulse width modulation on the Raspberry Pi. One is pulse width modulation, as I've described so far, being able to change the duty cycle of that pulse. The other has to do with running the servo, which is going to run off of pulse width modulation, but it's a little bit different how it works. This is the first class. This is the one that actually does the pulse width modulation. We have methods here to set the duty cycle and the frequency. Those are the ones we're most concerned with. As I said, I'm setting the frequency to 100 hertz, so your eyes can't detect the flicker. And then I'm going to vary the duty cycle, and you'll be able to see the bulb glow and not glow, or go on and off slowly rather than just like it was doing it before. Then we have the servo code, and I'm going to show you the servo here towards the end, but I just wanted to show you the module real quick here. Very much the same thing, it's just different files we're writing. We set the servo a minimum and maximum. When we set up, no, the minimum is always 0. Sorry, got lost there. Was thinking of something else. You set the maximum of, this servo goes 180 degrees, so we're going to pass in the maximum of 180 degrees. And then you can set the angle in there that you want within that range that you want the servo to point to. The angle, all you're doing here is same as before, writing a file. Servo max is the file we're writing to set the maximum, and servo is the name of the file that sets the angle. Everything else in here is just convenience methods. Set the servo all the way to the left, set it to the center, set it to the right, increment it left and right. That's all we're doing there. So let's run the servo, or not the servo program, but the pulse width modulation program. And our LED should be making a little heartbeat thing there.
Oh, yeah, nice.
The code to do that, very simple. We just set up the pulse width modulation, 100 hertz. Duty cycle is 0 to start with, so it's off. Make sure it's turned on, and then we're going to cycle through really fast and change the duty cycle from 0 to 99, and then back it down from 99 to 0 in half the time. And then keep doing that over and over again to get the interesting effect. Okay, now it would be nice to be able to do that with a knob. We've got a potentiometer right here that we can turn, and we'd like to vary the brightness of that LED with that knob. But as I said before, the pins are digital. To make that work, we're going to have to use a A2D converter. An A2D converter is going to take the voltage level and it's going to convert it to a series of bits. In this case, I'm using an MPC 3008. Has 8 input channels, 10-bit resolution, so you're going to get in values from between 0 and 1023. And it's controlled through SPI. SPI is a interface protocol. SPI can be a little tricky if you haven't seen it before. All I really have to do is send out the command to say read channel 0, and I get my bits. However, figuring out what the command is, I got to read the data sheet for the MPC 3008. And from looking at this, it's clear to the most casual observer that this is the command. These are the bytes that you would send to read channel 0. What that is you got a start bit. I don't know what that stands for, but basically you have to have two bits that show that it's starting. The next 3 bits are the channel we're reading. In our case, it's 0. Then you have to have 12 bits that are they're placeholders for the data that's coming in. There's a null bit, the 10 bits that are coming in, and the other bit, this is a little strange to explain because there's actually half a bit in there that you have to account for. Well, this information, you're shifting out these bits on the leading edge of this clock signal. And the information is coming in as you shift it out on the lagging edge of the clock signal. So there's half a bit there. So that's what all these zeros are for. Then we've got to pad it out in the front, so we have 3 bytes. And that is the command that you would send.
So how was the clock referenced? How was on the A2D converter?
Mm-hmm.
You have to have a clock reference that
Well, you do that. You do that by pulsing one of the pins. So your code. Now we're doing it through. This is hardware SPI. You can bit bang it. You could use any of the pins and do this. But again, Linux is not a real-time operating system, so your timing will be a little bit off. Oh, you can still do it. Just you send out a string of zeros by pulsing the clock while this is low.
Okay, I got it. Yep.
And actually, as it says here, don't care. Those don't actually have to be zeros. It doesn't matter what you send it. You're basically pulsing the clock in order to get the data back. The important part is that you send it 2 start bits and then 3 bits to tell you what channel to read. The other bits don't matter.
If you have a string of zeros, you'll have clock slip eventually, right?
Of what?
If you have a string of zeros, won't you have a clock slip eventually?
Not sure what you mean.
So for the Raspberry Pi to read in the bits that come from the A2D converter,
Right.
it's going to have to read them in sequence at the right timing.
Right.
The A2D converter sending it.
But it's determining the timing. It's determining the timing because it's what's pulsing the clock. if the clock changes frequency as you're doing this, it'll still work. So it's not a clock at a particular frequency. You determine how fast you're going to read that data in by pulsing the clock.
So 0 is
Yeah.
denoted by going from high to low then, is that?
Yes.
Okay, that makes sense.
Okay. Of course, I've written a little MPC 3008 class to handle all this. And it's simplicity itself. I went through and figured out what all the bits were to read the 8 channels. They're up here, so it can access them. You read a channel just by packing up the bits. You send it out through SPI transfer N, which is one of the functions from the device BCM 2835 module. As soon as you do that, the buffer that held the bits is going to have the answer in it. What's kind of interesting though is you didn't pass a reference to that variable. You just passed in the variable and it changed it anyway. That's because you can do that when your stuff's written in C. You don't have to follow the Perl rules.
You can do that in Perl.
What's that?
You can do that in Perl too.
I know. Still, it surprised me the first time I saw it.
Not normally considered a good idea.
Yes, but it does it here. Program that actually we're going to use here. What this is going to do is, as I said, read that knob that I'm going to turn, and it's going to set the LED to a value or a brightness level based on where the knob is. Set up my PWM, my pulse width modulator, just like before. There's my A2D converter. And read a channel. Set the duty cycle to that. The rest of this is setting it's looking out for jitter. If you just sat there and watched the values, they'd change by themselves. You bumped the table or just looked at it funny, the values would change. What I'm doing here basically is effectively removing bits from the A2D converter, giving it lower resolution.
What causes that jitter? Is it the chip itself?
No, it's the fact that the voltage isn't constant. This is just a slider on a piece of carbon, I think is what's in that potentiometer. So if you bump the table, it moves a little bit. If the temperature changes slightly, it moves a little bit. Breathe on it funny. Look at it sideways, it'll move. And the only reason I added that was because when I run that, it's going to display the value that it found. I didn't want it to scroll off the screen that fast. So I made sure it changed a lot before I did it. Okay, turn the knob, the light gets brighter. Turn it down, it gets dim. It's magic, kind of.
I don't know what to watch the numbers on the screen with the light.
Ooh. Yeah, look at that, numbers on the screen. Okay. As you can see, I'm getting towards the end. I've gotten lazy with my slides. Don't have much to put on the slides. It's all out here. I just did that, didn't I? Okay. Now, last thing I want to talk about is the motor. If you're going to make your robot walk so it can dominate the world for you, you're going to need motors. All kinds of different kinds of motors. What I've got is a servo motor that you can set to any of several positions. This is a 180-degree servo motor. Some of them will go 360 degrees. This one only 180. I already showed you the servo motor class. Nothing else to look at there. I already showed you the servo motor class, so let me show you the program. Okay. There's that little chunk of code that runs it as root, Brian, in case you were worried.
Yes.
Yeah. Set up the servo. We pass in we're using the Servo class, pass in the maximum angle we can do, the angle we want to set it to, activate to turn it on. Now we're going to prove it works just by making it go, making a little flag wave for you. And then I'm going to set up some buttons, just like we saw before. And then I'm going to use those buttons to increment the position of the servo. So let's see if that actually works. There it goes.
Will it walk my dog for it?
Middle button puts it in the center position, and then this button increments one direction, this button increments the other, and now the world is dominated.
One angle.
Actually, I had one more thing to show you. Well, just before we set up here, I wrote another program, which I won't bother showing you because you've seen all the components of it. Controls it with a knob. Woo!
Very nice.
Lots of fun. Any questions?
How hard would it be to put your Raspberry Pi on a quadricopter?
It'd probably be pretty easy. And I was talking about that with somebody earlier, but yeah.
Awesome.
But remember, it's not real-time operating system. You don't want it going off and doing something else when you're flying toward the skyscraper and you want to turn.
Well, you could do Arduino to do the avionics.
Mm-hmm. I would envision for that kind of thing an Arduino or two out there, and to handle those kind of tasks, the important stuff, and then let that be the brain and talk to the Arduino.
Cool. And the Arduino could accept it with the GPIO.
Pardon me?
You could talk to Arduino, you could hook it up to the GPIO.
Yes, talk to it through the, pointed out those serial ports earlier. You can talk to it through that, or you can, well, the Arduino works in 5 volts. You have to do the level conversion. This is 3.3 volts, but it'd be possible to make that work. There's some of the resources that I used here. Adafruit.com is where I bought the Raspberry Pi and a lot of these parts. They don't have them in stock right now, but nobody does. It's hard to come up with a Raspberry Pi these days. But that's actually an excellent source for these parts and tutorials. They have, actually, Occidentalist is made by Adafruit as well, and that's one of their tutorials, is how to install it. But they also have basic through advanced tutorials on doing all kinds of things with the Raspberry Pi. CPAN page for the module we talked about, and there's a link on there to the C library. And there's a very interesting article here on SPI that I had to read several times before I could explain SPI to you guys. And I already asked if there's questions, but I just came to it on my slides, so I'll ask again. Any questions? Well, thank you for coming, and it's time to wake up.